Hey everybody. Today we're talking about infinite limits. Let's start by looking at the function f of x equals 1 over x squared. Now, obviously, x equals 0 is not in the domain of this function. We can't divide by 0. What about the limit as x goes to 0? As x gets closer and closer to 0, this function is getting larger and larger, growing without bound. We can see that from the graph, or algebraically. The denominator is getting smaller and smaller, the numerator is staying the same, so it's growing without bound. We have an infinite limit here. Here's the notation. We write limit as x goes to 0, f of x equals infinity, to mean that as x gets closer and closer to 0, f of x is growing without bound. A little more technically, this means that we can force f to be larger than any value that's given to us just by restricting x to be sufficiently close to 0, but not x equals 0, of course. One thing to bear in mind, this is a situation where the limit as x goes to 0 of f of x does not exist. Remember, a limit exists if the value of the function approaches some finite number. And infinity is not a number, it's an abstract concept. Here's another example. Y equals 1 over x. Again, x equals 0 isn't in the domain here. We need to look at limits. In this case, though, the behavior of the function is different on the left and the right of 0. We should be thinking about one-sided limits. The limit as x goes to 0 from the left of f of x is negative infinity, and the limit as x goes to 0 from the right of f of x is positive infinity. We're getting different things from the left and right, so all we can really say about the overall limit as x goes to 0 of f of x, is that it does not exist. We can't be any more specific than that in this case. We can now give a definition for a concept that's familiar to us from pre-calculus, a vertical asymptote. A vertical asymptote is an x value where the function has an infinite limit from one side or the other or both. So, we're going to have a vertical asymptote at x equals a if the limit as x goes to a from the left of f of x is infinity or minus infinity, or if the limit from the right of f of x is infinity or minus infinity. You need at least one of those things to hold in order to have a vertical asymptote. Here's a graphical example. We have vertical asymptotes at x equals -1 and x equals +2. Visually, these are vertical lines that the graph seems to be getting closer and closer to as x approaches those values. Now we can see that these are vertical asymptotes using limits. At x equals -1, the left-hand limit is positive infinity and the right-hand limit is negative infinity. So both one-sided limits are infinite in that case. At x equals 2, only one of the one-sided limits is infinite, the left-hand limit. The limit as x goes to 2 from the left of g of x is positive infinity. Now, the limit from the right is finite, it's 2. However, we still have a vertical asymptote in this case. All we need is for one of the one-sided limits to be infinite. Now, we know from pre-calculus that rational functions, one polynomial divided by another, have vertical asymptotes whenever the denominator is 0 and the numerator isn't. We can now be a little bit more specific about that using limits. Here's an example. Find all vertical asymptotes of x plus 1 over x squared minus 4. We know from pre-calculus that we have vertical asymptotes at x equals plus and minus 2. At each of these values, the denominator is 0, but the numerator is not. Let's explore this a little bit more by looking at one-sided limits. And let's just do x equals 2. So we're going to be looking at the limit as x goes to 2 from the left to start of this function. I've started by factoring the denominator, x squared minus 4, as a difference of squares to get x minus 2 times x plus 2. Now, when x is very close to 2, the numerator is going to stay very close to 3. 2 plus 1 is 3. The denominator, however, is going to get close to 0 because of the x minus 2 term. The result is going to be a situation where the numerator is going to stay finite. It's going to stay close to 3. The denominator is getting closer and closer to 0. So overall, the entire fraction is going to get very large. For instance, when x is 1.999, f of x is negative 749.94. Therefore, we know that this limit is going to not exist. It's going to grow without bound in one direction or the other. In this case, we can say more, though. Since we have a one-sided limit, we know that x is less than 2. This is a limit from the left. And therefore, x minus 2 is going to be negative. Moreover, since x is close to 2, both x plus 2 and x plus 1, the other factors in the numerator and denominator of this expression, are both going to be positive. Overall, when x approaches 2 from the left, we have a positive over a negative times a positive, so this is always going to be negative. Putting these things together, we know that this function is going to be negative as x approaches 2 from the left, and we know that it's growing without bound because the numerator is staying finite and the denominator is getting close to 0. Overall, that tells us that the limit as x goes to 2 from the left of f of x must be negative infinity. Let's conclude by looking at the limit as x goes to negative 2 from the right. In this case, we are still getting a 0 in the denominator and a non-zero number in the numerator. Negative 2 plus 1 is negative 1. So we know that this thing is going to grow without bound as x gets closer and closer to 0. By the way, when I write negative 1 over 0, let's recognize that's not actually a number. It's just shorthand to describe how the function is behaving near x equals negative 2. In particular, a little to the right of x equals negative 2. Okay, so the denominator is going to 0, but the numerator is not. So the limit is going to have to either be positive infinity or negative infinity. We just need to figure out which by using this logic about whether the numerator and denominator are positive or negative. So x is going to be a little bit bigger than negative 2, and therefore our expression is going to be a negative over a negative times a positive, which overall is going to be positive. Putting this together with the fact that we already know that the limit is either going to be positive or negative infinity, we're able to conclude that the limit is going to be positive infinity. Here's a graph of the function, along with the two limits that we've already evaluated. We see vertical asymptotes at negative 2 and 2, as we would expect just by looking at the definition of the function. We determined that the limit as x goes to 2 from the left of f of x was going to be negative infinity, and we can see that here at the right-hand asymptote as we approach it from the left. Similarly, the limit as x goes to negative 2 from the right of f of x is going to be positive infinity. As we approach the left-hand asymptote from the right, the function is growing without